first one. So we are going to talk about how conductors behave in those cases where electrostatics is applicable, that is charges are at rest. Meaning of electrostatics is that charges are at rest. Static is. Okay? If they are moving, something else will happen. That we'll study in next chapter. Right? So first thing is for us to understand that if you have got an ideal conductor, then all these properties are going to be applicable, right? But what happens is that even in real, the metals that we see around ourselves, all metal objects, they are very very good conductors. So it's like they are near ideal. Okay, so although these are said to be ideal properties, but even in real life they work almost the same. Almost, right? There is very little difference sometimes. Okay, so first one is that electric field at the surface of conductor is normal to the surface. Electric field at the surface of conductor is normal to the surface. What that means is that suppose there is a randomly shaped, any shaped conductor, doesn't matter. Then over here, at this point, the electric field is normal. Here the electric field is normal. Here it's normal. Here it's normal. Like that, everywhere the electric field will be normal to the surface. Okay, the electric field will be normal to the surface. Now, why is it supposed to be like this? And there are a few ways to explain that. Okay, few ways. First of all, let's consider that it's not. Okay, it's like we're going to use contradiction to understand, right? That is, if we assume opposite, we see what happens, right? By assuming opposite. So suppose the electric field is not normal. Let's say it's like this. For example, it's an angle, not normal. Okay. Then do you realize we can make two components of this electric field, one normal and one tangential? Yes or no? Yes. Is this part clear? Yes. Two components of the electric field, normal and tangential. Now, is that if suppose tangential component is not zero, like this, here tangential component is there, then obviously metals or conductors have lots of free electrons. So suppose there is some free electron, then it will be acted upon by this electric field, and because of that there will be a tangential force acting on it in the opposite direction. Is that clear? Yes or no? Yes. Sure. Okay. Now like this, what this will mean is that it will make this charge definitely go around over the surface. It will make the charge move over the surface. Is that clear? It will make the charge move over the surface. You get what I'm saying? But first thing is that we are talking about electrostatics. So this definitely cannot be the case of electricity. So this won't be true. That is, ET will not be really there. That would mean if it is there, as long as it is there, the charge will move like this. Yes or no? Clear or not clear? As long as it is there, the charge will move. If the charge will move, then we are definitely not talking about electrostatics. On the other hand, En is not a problem. I'll tell you why. Because if you assume some shape of a conductor, let's say any shape, this is the shape of some conductor, then over here, if En is in this direction, over here it's in this direction, En is in this direction, and so on and so forth. Okay. Then we realize that it would try to push the electrons towards each other. Why so? Force on electron will be in opposite direction to the electric field. Yes or no? Yes. Yes or no? But it won't be able to go very far. It won't be able to go very far. One simple reason is that electrons cannot come together towards each other on their own. Is that clear? Someone has to force it from the outside, right? So the problem is that on their own these electrons cannot come close. They will repel, right? So even if it's like En is there, electrons will not go inwards. Did you understand? They will just stick to the surface. They will remain on the surface. Okay. There are of course more ways to explain that also. So as we proceed, you will find that we are going towards completion. At the end, every property will make sense. As we discover more or as we write more and more properties, everything will make complete sense. So this is the first one, of course, that we cannot have tangential component because that would only cause the electrons to go around or across like this on the surface. They will just keep moving. Yes or no?
Yes.
Okay, yes or no?
Yes.
Understood that? Definitely. Erase it all. Let's write what I have explained in short. Is that if ET is there, it would cause electrons, three electrons actually, three electrons to circulate on the surface, right? But like I have said, we are talking about electrostatics, so we will not talk about any case where charges are moving. So we are writing all these ideas based on the assumption or based on those cases where charges remain stationary. First one clear, right? Okay. Now let's present the other one, the second one. Is that if you would think it's related, there's another way to think. Suppose electrons, let's say, could move like this on their own. Suppose electrons could move like this on their own. There are either two options. When they move, either they lose energy or they don't lose energy. Yes or no? Come on, everything has only two possibilities. Either it will lose energy or it will not lose energy. These two choices. Yes or no, both possibilities are for a sentence. Either loses energy or does not lose energy. So now suppose you assume one, that it does not lose energy. Then what would happen? That will bring us back to first. If it does not lose energy in going around, okay, if it does not lose energy in going around, that means that if you set up electric field once, then the electrons will just keep moving and moving and moving and moving forever. Yes or no?
Yes.
Do you think that's true? You know that? Clear or not clear? It's like if you take, let's say, a metal object, a ruler, and a magic charge layer. We can charge objects by so many ways, right? So let's say this is a ruler, and we bring some charged object close to it. So we are giving electric field.
Yes.
The moment you start that, and if it is not zero, the electrons will start moving on the surface again and again, and then you remove the charge. The electrons will still keep moving. Because once electrons move, they have kinetic energy, and you said that if they are not losing energy, that means they just keep moving forever. પછી આને ઓર્ડર તો કરંટ લાગે because moving electrons make current. Yes or no? Moving electrons make current, roughly speaking. બીજી ઘણી details છે, but that's true. If electrons are moving, there is a current. Is that okay or not okay?
Yes.
So it's not like that. So what we are thinking is that it is impossible to actually set the electrons to start moving like this. Is that okay? The truth is they lose energy. Really speaking, they lose energy in a resistance here. Do you remember resistance? You would have studied resistance in 10th standard. When charges move, there is something called resistance. It tries to oppose the flow of current and wastes energy. Never mind. So coming back to this, so because we are talking about ideal case, we are going to consider that they do not lose energy, and if they do not lose energy, there is only one possibility that electric field can never become tangential, because if it becomes tangential even once, then what will happen? The electron will start revolving around the surface. Clear or not? Now that itself brings us to the second case. Because it's an ideal conductor and we have assumed that electric field is always normal. What is always normal to the electric field? Equipotential surface, yes or no?
Yes.
Everyone, is that clear or not clear? Electric field is always normal to the equipotential surface. Clear? So that's to be used here. It means surface of conductor is equipotential surface. Did you understand the second thing? Or not clear? Yes or no?
Yes.
How can we say that? Based on first one. It's that if electric field is normal everywhere, that obviously means the surface is an equipotential surface. Clear? Now that also, combines with what I was telling you, that in an ideal case, electrons should be able to move easily everywhere without losing energy or without any change of energy. That is only possible if all the points are at same potential. Why? Suppose all the points are not at same potential. Let's say this is A and B. Suppose VA is greater than VB. So do you realize that when electron will move either from A to B or B to A, there will be some change of energy?
Yes.
Or not clear? Why will there be a change of energy? U is equal to QV. Clear or not clear?
Yes.
Sure, an electric field is conservative. So if electron will move from one point to the other point, potential energy will change, so accordingly kinetic energy will also change. Is that clear? Right? But like I said, in an ideal case, the charge should be able to move freely. Is that clear or not?
Yes.
So combining all this logic, I hope you understood this sentence, that surface of the conductor will always be equipotential. The biggest reason for that is the normal thing. That electric field is always normal to the surface, not tangential or not even at an angle, always perpendicular. What it the property तो याद है ना equipotential surface नहीं है ऊपर से आता है एक side. Right. Next. Number 3 now. Electric field in the body, don't write inside. Electric field in the body of conductor must be zero or is always zero. Remember, we are talking about electrostatics. Okay, this sentence is only to electrostatics, just like every other sentence. So, what does this mean? First of all, I want to explain what is body. One thing of body, where the solid is, that's called body. Yes or no? Sure? Okay? So please remember, solid part, that's called the body. So if you have got some solid, randomly shaped solid, okay, it doesn't have to be sphere or anything, it's a solid. Now I am saying that the electric field inside, in the body of the conductor is always zero, or has to be zero in electrostate. Why? Let's assume opposite, it will give us a good idea. Suppose this is electric field, let's say towards left side. Again, we are using the method of contradiction. Mundu vichariye benjo a problem. So let's say it was not zero. So there will be some free electrons around here, yes or no?
Yes.
Yes or no? Free electrons by definition means they are free to move. Okay, second point mother. Okay, we use that reason. So if electrons are free to move and electric field is left side, where will free electrons move? Towards right side. Clear or not clear?
Yes.
Everyone?
Yes.
भूल गया? First afternoon. याद है ना?
Yes.
Electric field left side. So free electrons will move towards the right side. Got it? Okay. we are talking about? That means this is not the case we are talking about. Yes or no? We are talking about that case where the charges remain stationary. Basically, equilibrium is established. Okay, basically equilibrium is established and the charges do not move anymore. Got it? They settle at some place. Not there. Understood? Because if it's there, charges will move. Clear? If it's there, charges will move. Got it? See, this leads to very strange behavior. If you put a point charge over here, how much is the electric field just inside this surface? Suppose this is a solid conductor. How much will be the electric field over here? It will be 0. ત્યાં ગમે એટલા ચાર્જ મૂકો ને આખી આર્મી કરી નાખો ચાર્જની તોય કોઈ ફરક પડતો નથી. The electric field inside it in equilibrium case will always be 0. That is the first of all, when you put this charge, things will move a little and then they will settle in equilibrium. So once they settle, we are talking about electrostatics, and in that case over here the electric field will become 0. Got it? Yes or no? Right? There are more details to come here exactly thigh cable. Right? Okay. The answer to that question, what exactly happens in such a situation? Why or how could it be that the electric field becomes 0? To explain that, I'll use a very simple shape and a simple case, and the similar relation applies everywhere. Suppose this is a cuboid. And we take this cuboid, it's made up of conductor. It's a solid body, it's a conductor, alright? And we put it in a region where already, suppose there is a electric field everywhere. Okay, here voltage field line is draw karo. Okay, they are everywhere. Got it? So the moment you put it, there are free electrons inside it. Where will they start moving? Let's assume, just as we put, where will the free electrons start moving? Towards the left side. Clear or not? That's not electrostatics yet, because we are saying that charges are still moving. They are rearranging themselves. Okay, they are adjusting to the effect from outside. So free electrons will start going towards left side. Will all the free electrons go towards left side? No. You see, the moment one free electron reaches this side, obviously along with that we'll have one ion, positive ion on that side. Yes or no? Yes. Clear or not clear? Sure? Yes? No?
Yes.
What does this do? Because of one positive and one negative charge, do you realize that there will be a little bit of an induced field from inside? What do you think of induced? We are giving this field from outside. You can possibly call it E0. Okay, we are giving that field from outside. But as a response to that, polarization has occurred. What do you mean of polarization? Charges have split. That's called polarization in a very simple way. Okay, બે વસ્તુને separate કરતો, that is called polarization. So what has happened? Polarization has occurred. Negative charge, little bit of negative charge has settled here, and little bit of positive charge has settled here. But you know that charges always create their own electric field. Yes or no? So now at this point there are two fields. Which two? One is E0 from outside. Superposition principle. Superposition principle. E0 from outside. What is EIN? It is the induced electric field. Inside what is it? Induced. Okay, EIN stands for induced. Induced કોને કહેવાય? ટચ કર્યા વગર કંઈક કરો. This electric field, we are not touching anything here. So it charge separate થઈ ગયા means we are inducing. યાદ છે ને method of induction, charging by induction. આ થોડું કેના જેવું છે? એમાં આવું થતું ધ્યાન કરો. There were two spheres. You bring a rod, the charge is split થઈ જાય. You remember that?
Yes.
You know? Clear or not? So here we have got these two charges separated. So it creates a little bit of opposing field. But still, if only one or two charges have settled on the surfaces, E0 is definitely going to be more than E inside, or E induced. Clear? Okay, so what will happen? Still, the net electric field is towards the right side. So some more free electrons will have chance to go. Yes or no?
Yes.
Make sense?
Yes.
But as the number of free electrons or charges settling on the left side increase, the induced electric field will also keep getting stronger and stronger and stronger and stronger. Clear or not?
Yes.
Let's talk of a point when both become equal. Suppose at some point of time, charges were flowing and now we are at a critical juncture over here that E induced and E0 have become exactly equal. E induced and E0 have become exactly equal. What will happen at this time? Now if there is a free electron here, will it be able to go towards the left side? Yes or no?
No.
No? Why not? Why not? Because the total electric field is zero. Clear or not? Sure. So now will polarization process continue or will that process stop?
Stop.
Stop. So now charges will not move. Is that clear or not clear?
Yes.
Charges will not move. Okay. And what is the total electric field at this point? Zero. Welcome to the world of electrostatics. Okay, you have reached your destination. What's that destination? Now charges are not moving. And what is the electric field inside that body? Zero. Did you understand? Both will happen at the same time. The moment the electric field becomes zero, charges will stop moving. Is that clear? So when it's about electrostatics, what we have is that there is an equal and opposite induced electric field as there is external field. Did you understand?
Yes.
Until this happens, charges will move. And in a metal actually has infinite polarization capability. વધારે ટેકનિકલ વર્ડ છે અત્યારે ઇંગ્લિશમાં સમજો પછી ફિઝિક્સમાં સમજાવ. I'm saying that metal can have infinite polarization. તમે કરો એટલું પોલરાઇઝ થતું જાય. Okay? There is no limit to that. At one point though, the external field and the induced field due to polarization will become equal. There the process has to stop. Is that clear? So then at every point inside this conductor, what will happen? The electric field becomes zero. Clear or not clear? Yes. Got it completely? This is true for all shapes and for all kinds of conductors in all kinds of electric field. Okay, even in uniform હોય તો થાય, cuboid હોય તો થાય, sphere હોય તો થાય. No, nothing, no conditions whatsoever. This is always true if you are talking about electric field. Have you understood the third? Yes or no?
Yes.
Sure.
Yes.
Okay. Again, why are they zero? Because charges will flow, these two cancel each other at every point. Let's go to number, which is directly linked with number 3. Excess charge cannot be in the body of conductor. It has to be on the surface. Excess charge cannot be in the body of conductor, it has to be on the surface. Okay. So we will use number 3 to understand number 4. Again, if you are talking about electrostatics, what is happening is that the charges will all settle as far as they can go, right? Either okay, under and the under draw karo ke bahar draw karo ke surface is just thin. Do you remember what meaning of the surface? Sheet, yes, sheet has only one side. જે છે એક જ છે, આમ ગણો કે આમ ગણો. Okay, just like that, surface is an imaginary concept, isn't it? Yes or no? So when we say that charges are on the surface, So asking whether they are inside or outside is a useless question. Does that make sense? Yes or no?
Yes.
Yes or no? Appu. Because if you think of last line of the atoms, you get what I'm saying. Consider the last line of the atoms. Those will have charges. The last line of atoms say, are they inside the surface or outside the surface? They are the surface. Is that okay? They are the surface. So charges are at the surface. Is the proper word. On the surface करता है थे, whether exact ना कोई, the charges are at the surface. Okay. Why am I writing excess? Okay, and why can they not be inside, away from? First of all, what's the meaning of excess? Excess means extra. See, charges are everywhere. You should not forget that. There are hundreds or thousands of billions of charges inside your body also. Yes or no? No. Some body में atoms है कि नहीं? Do atoms have charges inside them? Yes or no? Protons, electrons, they are there. Correct or not? They have charges. But yes, what is the total charge of an atom? Total charge of an atom? 0. It does not have excess charge. What is the meaning of excess? Unbalanced or extra. Clear or not clear? Sure. So we are saying, first of all, the meaning of this sentence is that extra charges or unbalanced charges cannot be anywhere inside the body. They are at the surface. Right? Let's prove it using point number 3. We already know that everywhere inside this electric field will be 0, in which case in the case of electrostatic. So suppose I will take a Gaussian surface. Over here. Okay, to remind you all, Gaussian surface is an imaginary surface. It can be of any shape. Right? And here also I am drawing a random Gaussian surface. Because electric field over here is 0, the flux will be 0. Yes or no? Yes or no? Sure. For a closed surface, flux can also be found as sigma q enclosed upon epsilon 0. So that would mean for this surface, the enclosed charge is 0. What is surface draw करी sir? You might say possible that there is one extra charge here, means suppose plus 1 coulomb charge here and minus 1 coulomb charge here. Isn't it? Then also this would be 0. Sorry, your sentence is wrong. Isn't it wrong? If we take a Gaussian surface like this, then is it not possible that the total charge is 0 like this, that there is one extra charge here and one extra with excess charge here, but positive and negative? But our sentence to you it is only where? At the surface, not in the body. Don't worry. Now it's time to do something very interesting. Here I have drawn a randomly shaped Gaussian surface. Okay. But electric field is 0 everywhere, yes or no? Yes. So there is no need for me to draw such a large surface. I will draw a microscopic Gaussian surface. Did you understand? Yes or no? Yes. See, Gaussian surface is imaginary. So does that mean can I draw a Gaussian surface which is probably even smaller than the size of a nucleus? Yes. Okay, so that would not be right quantum mechanically, but anyway. So the idea is that if you are thinking that if you draw a Gaussian surface, then there can be two charges like this, then I am going to say, well, let's make the Gaussian surface smaller and smaller and smaller and smaller. What will happen? It's not 0 just for this surface. It will actually be 0 for all surfaces. But electric field is nothing. The flux can there. Yes or no? Yes. There is no electric field anywhere. So the surface draw karo. What's the flux for this surface? 0. That means the charge inside is 0. Is that clear or not clear? Right? You can draw a surface of any shape, any size. The flux will always be 0. That means charge for every combination is always 0. તમે એવું કહો કે સર આવી રીતે હશે એટલે તમારે 0 આવશે તમને ખબર ન પડી. Yes or no? ચલો માની લીધું આવી રીતે છે. તો હું અહીંયા Gaussian surface ડ્રો કરું તો 0 ન આવવું જોઈએ ને, પણ 0 આવે છે ને. Do you first of all accept the fact that it will always be 0? because electric field is not there. So જો તમે આવું ચાર્જ ડિસ્ટ્રીબ્યુશન રાખ્યું હોય and if I draw a Gaussian surface like this one, smaller one, then the flux should not be zero. It's a contradiction. Yes or no?
Yes.
So what's the way to avoid this contradiction? Simple. Positive and negative charge should always be at the same place. So the contradiction jai. Yes or no? Positive and negative charge should always be at the same place. But if positive and negative charge are at the same place, they are balanced. They are balanced. Where is the excess charge? It's not there. So that's what I'm saying. Excess charge is only at the surface, not in the body. Is that okay? Anywhere. Because in the body, everywhere electric field is zero. Did you get that?
Yes.
Right? So this is actually true for every Gaussian surface in the body. Right? For every Gaussian surface in the body, this is true. That's why charges cannot be anywhere in the body, they have to be at the surface. Got that? How can we know that they are at the surface? Suppose change nahi to, then there is a very easy way. Suppose you take a Gaussian surface like this. We know that electric field outside is there. In the body it's not there. समझ पड़े है? Suppose a negative charge है तो electric field आमा. Yes or no?
Yes.
Clear or not? You see there is incoming flux. So that means flux is negative. That means whatever charge is here will be negative. આ ચાર્જ ખબર ન હોય તમને તો એ તમને આવી રીતે ખબર પડી જાય. આ ફિલ્ડ લાઈન છે ને બહારની ફિલ્ડ લાઈન છે. Clear or not clear? So these field lines are coming in. Why are they coming in? That definitely means here there is some negative charge. Got that? So like this we can show that inside the body or in the body there is nothing, no charge. But at the surface there is definitely some charge. That's what the second part is. It has to be at the. Okay, see these are proper proofs to this. Probably you understood it intuitively also. That if we have a conductor and we put it in electric field, negative charge will start flowing towards one side and positive the other way. They will settle over there. Yes or no?
Yes.
I intuitive this. And that's what a proof is. Clear? Okay. Right? Let's go to the next. Which is once again related to 3. Number 5. Each point in the body of conductor is at same potential. Each point in the body of the conductor. I just want to confirm whether you have understood the meaning of in the body.
Yes.
Okay, let me draw a diagram to check whether your meaning matches. Suppose this is a conductor. Okay, hollow conductor. This is solid part. Did you get that?
Yes.
Okay, here I am drawing 2 points, 1A, 1B and 1C, suppose 3. Which point would you say is in the body of the conductor?
B.
Only B?
Yes.
Not A?
No.
Not A?
No.
Wait, complete. A is not in the body of the conductor. Is that clear?
Yes.
Again, body of conductor means the solid part. Clear? So B is in the body of the conductor. A is not in the body of the conductor. A is somewhere else. Okay? Fine. So this is what they were. So I'm saying that each point in the body of the conductor is at same potential. As the surface. As the surface. Why so? Point number 3 will help us. What have we proven? That in electrostatics, here, everywhere. What's the electric field? Zero. Sure. So if you go from point A to point B, let's say here's point A and here's point B. Let's find out potential. VB minus VA. What will I have? Negative integration E vector dot dr from A to B. So how much will this be? To make it, yes, zero. Electric field is zero everywhere. Yes or no? So potential difference is also zero. Okay. But there you can do not just for any 2 points inside. You can also do it if point A was on the surface. And ત્યાંથી electric field પૂરું થઈ. Electric field is not inside. Does that make sense to you or not? Okay. Even if you take A on the surface, right? As you come inside, the electric field is not there. What if electric field inside in the body of the conductor is zero? So as you go from A to B, there is no electric field. Did you understand the sentence completely? That we have VA is equal to VB. Okay or not okay? Right? So this leads to very strange things. Do it. So apply karo jo. Let me give you one example. Suppose you have some solid metal sphere. Suppose you have some solid metal sphere which is fixed. Which is fixed. Okay, by let's say someone is holding it in their hand by using some insulating handle. You understand that? Yes. Okay, so this is fixed. It's not going to move. Suppose some charge is given to this solid metal sphere. Positive charge there. Positive charge is given to the solid metal sphere. Then, here we have got point C, here we have got point D, and here we have got point E. Then which point has least potential? Which point has less potential out of all this? Sorry? अरे E आवे, तू ना E जावे, मजाक मत करतो. हाँ तू. Do you remember due to a conducting shell, what's the potential? A shell you behave करे ना, even if it's a metal sphere, yes or no? Because all the charges stay on outer surface. So this is like a shell. Yes or no? Yes or no? Sure. Everyone get there? Yes, no. Yes. Do you remember the graph of shell, potential of a shell? याद में तो जो अच्छी को सुना करे उधर ही है मैं sorry bullying no problem we have done it for electric field yes or no okay gravitation માં તો કરે તો પણ હવે તમને યાદ માં કઈ છે બરાબર એ તો તમારી નોટ્સ માં નહીં okay where is the electric field zero here at C 0 or not 0 at D 0 sure yes okay at E not 0 fine electric field lines will be normal to this sphere and they will go out like this yes or no yes sure so which point do you think has more potential D or E E has more potential logic बाकी थोड़ा जरा पता what logic are you using for saying E has more potential yes करो जो बेटा बेटा C D E करो reason बोलो reason see are electric field lines going like this so E करता तो आ point નું potential વધુ નહીં હોય yes or no yes or no yes sure yes I am saying that suppose we take a point F here F will have more potential than E yes or no yes sure yes okay but read this point above VF and VD are going to be same yes or no એટલે કહું થિયરી માં હાય હા કરી બહુ ઈઝી છે પણ એ વસ્તુ સમ્પ માં યુઝ કરવી ઉપર શું લખ્યું છે ઉપર every point in the body of a conductor is at same potential આમાં conductor છે કે નથી છે ને હા તો હવે એનો શું મતલબ VC is equal to VD is equal to VF clear or not yes or no yes sure જલ્દી નો ખબર પડી metal sphere means conductor all points are at same potential. No problem. Is that okay? Fine. Now field lines are going from F to E. That means what? That means what? E is at lower potential. Then F. Clear?
Yes.
So which point has least potential? E. So was that clear?
Yes.
Yes, no.
Yes.
Maths તો યુઝ ન કર્યું ફોર્મ્યુલા ને એવું હોય તો એનાથી એ થાય પણ એની કઈ જરૂર ન પડી ગ્રાફ હોય તો ગ્રાફ થી got it? Absolutely clear.
Yes.
Okay, હવે હજી ટ્વિસ્ટ કેમાં ચાર્જ હતો એટલે કન્ફ્યુઝ થઈ ગયા
The body.
in the body હમણાં તો ક્લિયરલી તો સમજાયું in the body કોને કહેવાય okay try this now. Suppose once again there is a randomly shaped metal object. Okay, right? Here is a point A, and here is a point B, right? And here is a point C. This object is neutral overall. Neutral, that is, it has no charge total. Okay, it is not a charged body, but yes, it is fixed using some insulating handle. એટલે આ move નહીં થાય can you see? Is that clear? Now over here you put a little charged sphere, positively charged sphere, which is also fixed. Okay, which is also fixed like this, and they are a little bit close to each other, not touching each other but close to each other. There again, let me clarify what this is. This is a metal object of some random shape, and this is some little sphere which has charge. Now, question is, order these potentials in increasing way. One, increasing order of potentials for A, B, and C. Increasing order of potentials for A, B, and C. Come on. Same. Sure
Yes.
or not?
Yes.
A નજીક નથી. A નજીક નથી. A નજીક નથી. હું પૂછું તમને, is A closer to the charge or not?
Yes.
So potential વધુ નો આવે? નો આવે. તો એટલો આવે. VA is equal to VB equal to VC. પણ આ વસ્તુ અત્યારે તો યાદ છે. પછી એક્ઝામ માં આવું દેખાશે ને એટલે સ્ટ્રોંગ ઇન્ટ્યુશન ઇફેક્ટ થશે. આ નજીક છે પોટેન્શિયલ વધારે આવે પૂરું થઈ ગયું. બી વેરી કેરફુલ. ગોટ ઇટ? આ બે કેમ ફિક્સ કરવા પડે ખબર પડે? ફિક્સ ન હોય તો શું થાય? They will at when. Okay, so it's necessary to have them fixed. Okay, there are more properties to study. We will continue with the list the next. એટલે આ બધું યાદ